Let me begin with what I'm going to be convincing you here, that emerging key value storage devices enable providing better data reliability in many cases at competitive or lower cost on throughput than traditional RAID for block devices. So what are key value storage devices? These are devices with key value interface instead of the traditional block interface. So the key value devices internally, in addition to what it already used to do, have key lookup logic and indexing that is going to have a mapping between the variable length keys to the location of where it resides. And in addition, it can also support iterating over the keys. And there is the user applications directly can store, retrieve, and delete the KV pairs using a very thin user space KV library. So in this work, we use prototype NVMe KV SSDs from Samsung. They use the same hardware resources, the same hardware as the enterprise grade block SSDs, but with KV firmware. And we support currently 4 to 255 byte keys and up to 2 megabyte values. And for more information, if you're interested on the ecosystem software, please check out this link. So first, what I'll not be going into in this work is KV IO throughput versus block IO throughput. That's not what we are comparing here, because it's actually not an apples to apples comparison. There's more internal tasks to do with the same resources. And the KV IO throughput depends on the value sizes, the key sizes, and prototype firmware. We'll not be going into more of that details here. And you can also ask, how about adding more resources for KV SSDs, things like that, because some people have been talking about that. That's an interesting question as well. There's also power, cost constraints, and all those things into picture. And should we actually do it? Do we need to do it? Those are all different questions as well. So we won't be going into that as well. So if it does not always beat block SSDs, why should I care? For more about that and for KV to KV SSD comparison, we have another paper, and it also covers some of the internals, so you can take a look at that. It's at Cisco. A little teaser here is when you add more devices, it can get much higher throughput with very limited CPU requirements. So here, in this work, for the data reliability requirements, we wanted to provide multiple options with different trade-offs, similar to what RAID does for block storage devices. And all these options should be able to support variable length keys and variable length values. And we also wanted to preserve the low host resource requirements of KV devices. And in addition, we also wanted to offer some flexibility to the users and coexistence of multiple options. So KVMD stands for Key Value Multi-Device. It's a hybrid data reliability manager for KV SSDs. It supports multiple pluggable reliability mechanisms. We'll call it RM from now on. And there's also multiple pluggable erasure code implementations. They are all in the user space. It sits between the user application and the key value library. And there's also an optional, you can have an optional data and metadata caching layer, which is not in this work. It is not implemented, it's not shown in any of the results. But I'm putting it in here for your imagination about how it could work. So the reliability mechanisms themselves, here is, what we have implemented is 4 different ones: hashing, replication, splitting, and packing. 2 of them, the splitting and packing, use erasure coding. Hashing does not add any redundancy, and replication just replicates. We'll go into each of them in detail later on. So before that is the modes of operation. The first one is just the standalone mode. You can be like, for all my needs, I just need one reliability mechanism. Say, I just need replication. You can just choose that, and you can be done with it. You don't need any coexistence. You can just choose that. And then the second one, which is the hybrid mode, is configuration file-based. you want to choose different reliability mechanisms for KVs in different value size ranges. For example, if my value size falls between 0 to 2 KB, I want to choose replication. If it's between 2 to 16 KB, I want to use packing, and later, bigger than that, use splitting, and all of them coexist in the same system, then that's in hybrid mode. And finally, the custom mode, you choose either one of the above, and then every single write, you have the option to choose a reliability mechanism. These are for known outliers. So you always choose packing, but for certain things you want to choose replication, you can do that as well. So what is needed to coexist in the hybrid mode for the RMs here? So we require each RMs to place the first copy or chunk of the KV pair on a primary device. Every KV has its primary device decided by the same hash function, and it needs to store that first copy or the chunk using the same key as the user key. So that device's primary information will be stored in its primary device. And the second is, if there's any other required metadata, it will be stored in the beginning of the value. So if the value, here it says full or partial, because if you are splitting it, it will be partial value. If it's replicas, it will be full values. To the front, you have an reliability mechanism identifier, erasure coding identifier, which one, because everything is pluggable, you want to be able to retrieve what was used to store this value with. And splits, I'll talk about splits soon. And checksum, every value stored will always have checksums associated with it, and any RM-specific metadata that is required. So in hybrid mode, every operation first requires a read, because some of the mechanisms might want to handle updates differently. So if the key value pair already exists, before updating, you need to know whether it exists. So first you do a read, and then you carry on with the operation, or you give it to that particular reliability mechanism. They'll deal with it appropriately. Then you go to the next mechanism. So in which case, the optional caching layer, which is not yet there, can help, but that's not what we are going to show in this result. And the huge object handling is because we have the 2 megabyte limit, but users could want very big ones. So we would, if it is bigger than the limit, we would split it and store it in multiple values, and that is what the total split is about. And the key also has metadata with it, which stores the split number. The first split will also always be 0, and then any RM metadata. So going to the reliability mechanisms, first hashing is straightforward. You just use the hash function, determine the primary device, and store it there, and all operations are directed to the primary device. And replication, you determine the primary device, and you store the replicas to its adjacent neighbors. Why adjacent neighbors? Because when a device fails, entire device fails, you need to recover it. How do you know what was stored in this device? How we handle it is we iterate over all the keys in its neighboring devices. When you iterate over the key, from the key, that reliability mechanism can determine whether this key should be, any part of this key, KV pair should be present in this device, and then it would recover it and give it back to you. So that's why we keep it in the adjacent devices. For replication, because this is once after it, you need to iterate the devices that's behind and forward, both sides. And so for the additional metadata, both of them don't require any key metadata, and replication, it just stores in addition how many replicas. Splitting is like what we talked about before. It splits the value into k equal-sized objects and adds R parity objects. Equal-sized, not always, because this is variable length, and you are using a pluggable erasure coding mechanism. Each mechanism might have a size constraint on it. So based on that, the size of individual chunks would be decided. So the final data chunk is very likely to be smaller size than the other chunks. So that's why, in addition to storing, as part of the metadata, in addition to storing the EC implementation that was used, we also store the actual value size. And for the actual parity calculation, zero padding will be done, but not actually stored in the device. And we also store K and R parameters. And sometimes, depending on the erasure coding implementation, they might also require some additional metadata to be stored, which also will be stored here. Finally, packing. This groups multiple KV objects, and it packs up to K different objects into a group. So first, any KV that comes in, the primary device is decided, and it will be stored as such in that primary device. And that device has the queue where what was stored. And from K different devices, you will be picking different KVs. Here, the ones highlighted in blue, key X, Y, B, and C can be chosen. And then those values are grouped together to add parity objects. And here, when you are grouping, they are all variable length, right? So you need virtual zero padding. The actual zeros will not be stored just for the parity calculation. And then the parity objects would be of the biggest size of these values. And those will be stored in devices that was not picked from. So they are all distributed. And now, because you are grouping different ones, you also need to know what other KVs did you group it with, so that when you need to recover something, you need that information. This adds some metadata. So this has additional metadata objects. So for the actual value itself, whatever metadata you are adding is very similar to the previous one. And the key metadata will be storing, if it is a user object, it's straightforward. And if it is a metadata object, which is the one that stores how many keys were packed together and what was the key length, keys, and what was the value sizes. We need value size again here because of the virtual zero padding. And that becomes the metadata object, and the parity objects has the identifier P to it. So these are all used when the entire device fails and you are iterating over neighbors to figure out what needs to be recovered. And the problem with this usually is, or in our current implementation very much so, is that when you need to update or delete a KV pair, there's dependencies. We have introduced dependencies. So you need to read the other ones. You need to either regroup them before you update this, or you need to update the parities and write it. So our current one is very simple, straightforward, synchronous operation. So our current updates are terrible. But you can improve it. So we'll go into the evaluation, and here we are comparing software rate, Linux mdadm-based for block devices, and KVMD for KV SSDs. 6 NVMe SSDs, the same ones, are used with different firmwares, and block for block firmware, and then our KV firmware. And right, so KVMD also has, for all the operations, it also has additional hash calculations, and every read will always verify the checksum. So we also have this checksum calculation and verification overhead for every operation going into it. And we have currently used ISAL library-based implementations for checksum calculation and read-Solomon erasure coding. So we'll go into the results. Because this is not apples to apples, we'll be seeing them in two different slides, the rate and the KVMD. And here, the y-axis on the one side is for the bar graph, which shows the throughput in KIOPS. And the other side shows the percentage throughput achieved in terms of the first option, which is striping with 4 KB chunk sizes. So that y-axis is for the lollipop plot, which is nothing but the sticks with the round lollipops on top of them, which are all in red. So if a lollipop is on top of a bar, it belongs to that category, right? So the bar's head, you'll have to look at one axis, and the lollipop head, you'll have to look at the other axis. I would like to direct you mainly to the lollipop plots because I want to focus here mainly on the throughput degradation. And all of these we have done with block sizes 1K, 4K, 16K, and 64K for different RAID configurations with 4K stripe size, chunk size, and 256 KB chunk size. And you can see from the figures that the writes, sequential write, random write, all the writes are terrible, really terrible, because of the read and write amplification that's going on, and probably due to the implementation problems in current Linux RAID. And for the writes, for the reads, they aren't so bad. And with the write configuration, you can see in the top 1K and 4K that they do have degradation. They are not up to par without using any any redundancy mechanism, but it should be because it's just straightforward read. But going forward, or with the right configuration settings, which is you need to fine tune and find out, you will be able to get pretty good read results here. Next is KVMD's cost on throughput. And here the one that we are comparing the throughput percentage to is none, which stands for each one we separately get the maximum throughput and just add them together. That's the none. And so one thing I didn't mention was the previous one, RAID, was we tried RAID, that was with FIO, and with that we tried with different thread settings from 6, 12, 24, etc. And 12 was the best, 24 was the best performing, so that's what the results were. And here we just have one thread per device, so six threads going on. And replication, the ones in the writes, the stores, these are all inserts. And the hybrids, as I said before, always include a read before you actually insert. But the read will return none here because it's all inserts, it's not updates. And because of that additional reads, there's a throughput a slight degradation from one without using the hybrid mechanism in the standalone mechanism. But if you look at the actual raw performance, you'll see that replication is as expected, that it's like, because it's storing 3 copies here, it's 1/3 of the throughput, roughly, and packing, even though we store additional metadata objects, it makes a little bit more difference in the smaller value size ranges because they are all similar value sizes. It's not similar, but still there's more I/O happening there and impacting it. But as the value size increases, the small additional metadata writes are not of a big impact and doesn't show up much. And it also has similar read characteristics as replication, so packing wins in that area. And if you look at splitting, because every single I/O you're converting into 6 I/Os now, it's going to reduce the throughput a lot. But the value sizes, as value size increase a lot, it doesn't matter because you are still getting good IOPS. So it's a trade-off, and with splitting, you also pay a performance penalty for reads. Because every single read, you need to read 4 different values, and then you'll need to combine them and give them back. So you also have to pay that penalty unless you are only reading part of the value, in which case you wouldn't. So it all depends on the user needs, which they want to pick. So updates and deletes. We also have mixed value sizes in the paper. You can take a look. And updates and deletes is, as I said, packing has terrible updates currently and deletes because it's all synchronous. And but replication and splitting has similar performance characteristics as what we saw before, the insert and the read. And this is just for 4K. And you can also see that the device characteristics itself, as of now, that's also changing, is that updating a key has roughly half the performance as inserting a key, but deleting is similar performance. So we'll go to how we can use that for future work. So the final thing is device rebuild scenarios. So when the failure of device occurs, here what we have done is we have just written like around 4 gigs of data to the device. So the actual user data is less, in which case when you're trying to recover the failed drive, if it is, in case of RAID, you're trying to recover every single block there, and that's what is happening. And because of the capacity increases, then it takes a lot of time. And with rebuilds, with the use with KVMD-based mechanisms, you are only recovering whatever data you have written and is live. And so that's why it takes lesser. Again, this is not a measure of whether this is the best implementation or whether it is the, because this is also again a synchronous recover one key at a time kind of implementation, but just to show the value of the having key value based recovery instead of complete device recoveries. So limitations and future directions is we do not have concurrency control right now. It's up to the applications right now. And the device guarantees that when you are concurrently writing, it will be one or the other. But what order they want and all that is up to the users now. But apart from that guarantee, what we have, because we are now combining multiple devices, we can also put that concurrency control somewhat into the KVMD itself, but we haven't, and that's one directions to look at. And similarly with crash consistency and consistency checking, we haven't gone into consistency checking and consensus protocol, etc. And data and metadata caching and packing performance. So one thing we are looking at is, or people could look at, is versioned updates, because all you need to do for versioned updates is add one more bit of data in the key, another metadata. It's just another version now. And that will take a lot of the pain points away from packing too, and you can provide concurrency control, crash consistency without affecting performance a lot. Particularly, in fact, in the what we saw earlier about the update, which is delete performance, instead of just updating something, you can insert something and delete the previous one, which will still be fine. So that is one area to look at, and the others ones would be automatic RM determination and even capacity utilization and how you spread out based on the value sizes. That's all areas we haven't looked at yet. So to conclude, we offer better MTTDL mean time to data loss than block SSDs in many cases because of reduced write amplification. Not yet for packing updates, but in most cases, it's much reduced write amplification than RAID, and which matters a lot for SSDs, which is better for MTDL, and faster device rebuilds because it's proportional to number of user objects. If you can recover something quickly, that means you're reducing the time window for another failure to occur at the same time, so that offers better reliability. And we also showed that the throughput degradation is either comparable to or lower than software RAID in most cases. And also we can offer much better flexibility to the users to directly control what they want. Any questions?
Hi, here, Umesh Maheshwari from Hewlett-Packard Enterprise. I have a question about erasure coding over small key value objects, which you call packing. You mentioned that you keep some metadata objects to help with the recovery in this case. And you can recover from full device failures by iterating over that information stored in other devices. But what about partial failures, which, for example, you try to read an object and its checksum does not match, which is presumably the more common case of failure with SSDs. The whole device might not have failed.
So the metadata object which stores which keys were packed together is stored in the neighboring devices. So when there's failure like checksum failure or any errors given out by the device or any such cases, you can read that metadata object which is in the neighboring device, and then from there you'll know which ones were grouped together, read them, recover this back.
But you need to iterate over lots of keys in those
No, in
nearby.
that case it's not iteration because it's the same key name as the user key name with an additional metadata byte that has the metadata marker. So you know the key name of the metadata object.
But in that case, you're going to have lots of metadata objects. So for example, if you want to do 5+2 RAID, how many metadata objects will you have?
So for each of the actual user 5, you'll have 2 additional metadata.
Right.
In addition, you'll have the 2 parity. The metadata is small in size, right? But the number of IOs this way has become very close to replication number of IOs, but the size is not.
Right. So you'll have 10 additional metadata objects and maybe +2.
So let's say 5+2 is 3 times 5 would be 15 plus 2 is 17, right?
Right. So there's a big explosion in the number of objects.
Yes, if you're doing 3-way replication, it's 5 times 3.
Well, even if you're doing just 1, 5 plus 1 will result in 11 objects total?
5 plus 1 is, yes, 11 objects, and if you do 2-way replication, it's 10 objects. So which is very close to it,
well,
but the actual storage cost is not close. Yeah. But the IO cost is. That's why we are showing the difference of how much does it impact, because these are small IOs that's going into it. It does have an impact, but it also does provide you flexibilities. But I'm not saying this is the only way to do it. There can be additional ways of combining these metadata objects in the future as well. That's one good area to take a look at.
Okay, thank you.
So I have one question. So
yes.
For your hybrid solution with a variable, KVIO size, right? So do you have any killer applications that can benefit from this solution? Some, typical applications.
Particularly for hybrid, you are talking about?
Yes.
So many people typically tend to use metadata KV separately from their user KV. They'll have their own metadata they'll want to store as separate KVs, in which case they have a mix of small and big objects, but they don't know how many is going on. It's really hard to judge what is the right mechanism. You can just say, but if you know the characteristics, you know that smaller ones is not gonna give you a big storage cost, but you still want good performance because that's the performance killer. You can make a choice to that. But you don't have to predetermine that. It can be automatic for you.
Okay, thank you. So let's thank our speaker again.